The final thing that I want to look at in today's lecture is a form of the first law for an open system under the condition of steady flow. Thus far, the majority of the treatment that we've looked at for the first law have been for closed systems or fixed mass systems. Now what we'll do is take a look at the first law with open system conditions. So remember, that's where mass can be crossing the boundaries. And we will restrict our treatment of the first law here for steady flow. And so that means that there will be no transients. We lose derivatives with respect to time that can sometimes be within the first law. So changes of state or of your process. So the form of the equation, we have heat transfer minus work, and we have the over dot to denote a rate. And then on the right-hand side of the equation, we have mass flux leaving the system multiplied by three terms. We'll have the enthalpy, the kinetic energy, and the potential energy. And then we subtract the sum of all mass streams leaving our control volume So that is the first law for an open system steady flow. The different terms that we have in the equation, Q dot is the rate of heat transfer. And remember, we talked about the definition of the direction, or what would be a positive term here, and we'll define it as being positive into our control volume. Work, that is work being done by the system. So it could be shaft work and electrical work, or the other types that we've been looking at. And we will use the convention with that being positive out of control volume. So we put the heat in, and that is positive. Work is being done by the system, and that is positive. And we also have, you'll notice we have enthalpy leaving and enthalpy entering. Sometimes, depending upon the way that our fluid streams work, we can sometimes combine, pull out the mass flow rates, and then we have the change in enthalpy of a stream being H exit minus H in, so that would be the enthalpy change. And depending upon the temperature change that you have of the fluid stream coming in and leaving, you can sometimes make the approximation that we talked about a moment ago, which is temperature exit minus temperature inlet multiplied by the specific heat at constant pressure averaged. And remember, this is only for ideal gases. And if you're dealing with a problem using either refrigerant or steam, use the tables from the back of the book. So I should say here, this is for delta T less than 200 degrees C. Steam R134A, use tables. And finally, in this equation, we have the mass flow rate. That's the mass flow rate into or out of our control volume. So So that's the first law for an open system. Now what we're going to do, sometimes you can simplify the form of this equation to single input, single output systems or devices. And there are quite a few that we will be studying in this course. And so consequently, that equation gets a little simpler. So common steady flow devices that fall within that single input, single output definition. Could include nozzles and diffusers. A nozzle takes pressure and changes it into kinetic energy to accelerate the fluid, whereas a diffuser will take kinetic energy and convert it into pressure of the fluid by decelerating the fluid. Turbines and compressors. In the case of a turbine, we're getting work out of the fluid, and the fluid is changing property or state as a result of that. Or a compressor, we're doing work on the fluid and it's also changing state, usually an increase in pressure and temperature. Throttling valves. We will see these throughout the course. And quite often all this is, it's just a valve where you have a pressure drop. They're not really the most efficient because you're losing energy. Actually, it's going into the form of thermal energy. And you're not getting any kind of mechanical work out of it. So they're not really the most efficient, but nonetheless we do use them from time to time. You'll see them in the refrigeration cycles and in some other problems. Mixing chambers, this is where we take two fluid streams and consequently it may not be single input, single output, but the modification to the equation that we just looked at, the first law, is not that significant because usually you have a single output coming out. And finally, heat exchangers. We can also sometimes use the form of the first law that we just looked at. So, simplifying the first law, it will remain the same on the left-hand side. So we have Q dot minus W dot. But then on the right-hand side, you can sometimes pull out the mass flow rate. And then you will have something like this. You have the change in enthalpy plus the change in kinetic energy plus the change in potential energy. And in this, 1 denotes inlet state, and 2 denotes the exit state. So that concludes today's lecture. What we've looked at, to recap, we've looked at the definitions of, or ways to calculate enthalpy and entropy. We've looked at the different forms of heat transfer and work that we may be looking at. And we also looked at the first law for an open system. Thank you very much.